Today I want to talk about two things. I want to make sure you understand how to find an inverse function, and then I want to show you how to graph logarithmic functions. So about those inverses. There are two steps you need to do, and that's it, just two steps to find an inverse function. So the first step I do is switch x and y, and then you can solve for y. For example, the function y equals 2x plus 3. First I'm going to switch x and y, and then I'm going to solve for y by subtracting 3 and then dividing by 2. You could also, if you wanted to, do the steps in a different order. You could first solve for x, and then you could switch x and y. If I have the same example and I first solve for x, I'm going to subtract 3 and then divide by 2. And then the second step is to switch x and y. And you notice I have the same answers for both of them. That y to the negative 1 doesn't mean a negative 1 power. It shows me that this is the inverse function. Here's another one. Y equals 2 to the power of x. If I follow those two steps to find the inverse function, I'm going to first switch x and y, and then I'm going to solve for y. Now, y is an exponent in this case, so in order to solve for y, I have to rewrite it as a logarithm. So log base 2 of x equals y. Notice that they are inverse functions. Y equals 2 to the power of x is shown in red, and y equals log base 2 of x is shown in blue. Okay, let's take a look at these logarithms. I have graphed here a few for you, log base 2 of x, log base 3 of x, and so on. Notice that they all go through this one point, this point 1, 0, and I'm going to call that my reference point. All parent functions, logarithmic functions, will go through this one point. Another characteristic is that they have an asymptote at x equals 0. The domain for all these, the x values, are from 0 to infinity. The range is from negative infinity to positive infinity. Another characteristic, and something that's easy to graph, is if you look at log base 2 of x, if x is 2, then y is 1. So I have the point 2, 1. Log base 2 of 2 is 1. Log base 3 of 3 is 1. Log base 4 of 4 is 1. So these are nice, easy points to graph. Okay, two ways to graph it, and I'm assuming the first way is how you did or you tried to do on your warm-up, and that is to make an x and y value from this function. So you had to kind of think about what values would be good to plug into my function in order for nice whole numbers to come back out. For example, 2, so that would be log base 2 of 2. So when x is 2, in this case, y is 1. Another example, another good point to plug in would be 4, because log base 2 of 4, which you can also write as log base 2 of 2 squared, would be 2. Hopefully you found another point, such as 8, which it turned out to be 3. But you don't have to stick with whole numbers. The x values, since it's an argument, can't be negative and it can't be 0, but it could be fractions, such as 1/4. So this would be log base 2 of 1/4, which turns out to be negative 2. So that's one way. You have to think about what x values will make this easy to graph. Another way to do this, in which I find it a little bit easier, is to rewrite it. So if I rewrite it as an exponent, it would be 2 to the power of y equals x. And in this case, I'm going to fill in my y values first and then solve for x. For example, I can pick 1, so 2 to the first power is x, and x in this case would be 2. So I'm still graphing the x and y value, the point 2, 1. Another point I can pick is 2, so 2 squared is x, x is 4. 3, 2 to the third power is 8, and so on. I don't have to stick to whole numbers. Or positive numbers. I can put in a negative number like negative 1, and it comes out to be 1/2. So after you find enough points you can graph, notice the reference point is there, 1, 0. That easy point 2 comma 1. The asymptote is there, x equals 0. Domain is from 0 to infinity. Range is all real numbers. Let's talk about transformations. So x plus 2 is a transformation, and as we noticed for all other functions, the plus 2 will shift the graph to the left 2. This minus 5 is another transformation. This is not part of the argument. It's outside of the x values. This is going to shift the graph down. So if I take a look at my parent function, and for every single one of the points that I graphed, I shifted every single one of those x points to the left 2, and every single one of the y values down 5, I'll have a new graph. Just remember, log base b of x. It's the parent function. There's no transformation. That reference point 1 comma 0 is there, and whatever that b value is, the y value is going to be 1. For example, log base 4 of x. The reference point is there, 1 comma 0. If I pick 4 for my x values, the y value is going to be 1. And here's what the graph looks like. The asymptote, x equals 0. Domain is from 0 to infinity. The range is from negative infinity to positive infinity. Think about how this graph would change. These 2 points that I have graphed here, I'm going to shift all my x values to the left 2 and all my y values down by 1. Not only have my x and y values shifted, but my asymptote has also shifted. It's been moved over to the left 2. Okay, last one. This one, it looks more challenging, but it's really not. If you remember that natural log is the same thing as log base e. So of course we have the reference point of 1, 0, and we also have that base and 1. So the base is e, which is 2.718, and so we have 2.718 comma 1. Think about how this graph, this transformation would take place. That minus 1 is a part of the argument. It's going to shift the graph to the right 1. The plus 3 is outside of the argument. It's going to move the graph up 3. It looks like the graph is stretched, but it's not. It's just been transformed. The new asymptote for the blue function is going to be x equals 1. And that's it. I hope you can finish your work now.